Hello. So I talk about hydrodynamical analogs of some quantum phenomena and also some other very related experiments from the best journals. So generally, this problem that at least Feynman said that we don't understand quantum mechanics, so we need some better intuitions, better analogs to maybe finally change it uh, to get some intuitions. And these experiments can get classical object with wave-particle duality. So like here, there is a shaker and there's some fluid, and there is a droplet which just jumps, walking droplet. And so we have the corpuscle, and each bounce generates waves around, so which acts as a couplet wave, as the pilot wave. Yeah, so we have both the corpuscle and the couplet wave around, and this way is similar to this de Broglie bomb, this pilot wave interpretation, and thanks of that, they get many quantum-like experiments like interference, double-slit, tunneling, object quantization, various ways, Zeeman effect, quantum statistics, CSSH, Bell-like inequality violation, also some different related experiments will be mentioned. Okay, so there are lots of materials. I recommend them all. Okay, so the first question is we would like to try to understand here is where is the boundary between classical and quantum world. So for example, if you have electrons around the proton nucleus, we say that there are wave packets, these clouds of probability. But if there is some backscattering electron, we treat it as a point. Yeah. So the question is, should we treat them differently? Is it classical quantum? Where is this boundary? So let's think about this simpler case, those couplet pendula. We can describe them classically with ordinary differential equations, or we can just go to this normal modes. So one normal mode is going the opposite way. One is together. Yeah. So in this normal mode base, the evolution is practically unitary. So we get already classical and quantum description of couplet pendulum. Then we can get to lattice, like crystals. We can describe it classically, or again go to normal modes, which are treated as quasi-particles in quantum field theory. So again, so we get the same, but there's different perspectives on the same system, classical and quantum. So now the difficult part is the continuous limit. So I will show the orbit quantization examples like here. So this couplet wave to our corpuscle has to become standing wave, because otherwise there will be some fluctuation which would like to radiate, finally leaving only the standing wave. Yeah. So also in quantum mechanics, we have this Schrödinger equation and find the stationary solution, the ground state or higher excited states. These are standing waves. So again, so here and here we search for standing waves, which are described with very, very similar equations. So again, we can see them both, and I will elaborate further. So this is for single particles, and what about multiple particles? So in quantum field theory, we use this perturbative approximation of Feynman diagrams, which is some very abstract description. Yeah, so here, if you have electron, there should be some electric field of this electron, magnetic dipole of this electron, angular momentum, and here we just have some abstract points. So this is only approximation perturbative, which would be able to ask about non-perturbative pictures. What are the fields represented by such Feynman diagrams? And for example, there are soliton models which also are able to reconstruct multiple particles interacting. Okay, so here is this de Broglie bomb interpretation, which is very simple, just substitution of this Madelung square root of some density times exponent of I times action divided by h bar. If you substitute to the Schrödinger equation, we get the continuity equation for the density as expected, and this classical Hamilton-Jacobian equation for the action, however, with this quantum correction, this Q, which depends on this interaction with this pilot wave. Yeah, so this is just the same as Schrödinger equation, just in different representation, this Madelung substitution, and we get classical behavior with this interaction with this pilot wave. So this is will be recreated in experiments. I will show. The problem is that it is only for a single particle. The question is what's happening for multiple, and usually it's said that we need a tensor product, what is very costly, especially for some simulations, but the experiments here suggest that maybe it's sufficient to have just one field. So this couplet wave is in one field which is shared between all these objects, and this way they get very nice experiments. So if it's sufficient, it will be great help for building much better simulations without going to higher dimensions, just everything in 3 dimensions. So the best experimental confirmation of Harlan bomb I know is this 2011 article with double slits, but measuring average trajectories of single photons in two-slit interferometer. So there are there is two slits. So we usually say that if you can measure which path it came, we get classical behavior. However, here they use only weak measurement. So don't get complete information. We need averaging over many measurements to get them the real information. The weak information here is encoded by this calcite, which encodes information in the polarization, which finally is measured, allowing them to reconstruct this very nice trajectories that first you have these two slices, and then there appears the interference pattern, and they say it is agreement with the Broglie bomb theory. Okay, so why in this this experiment we have the shaker? Yeah, so we need some external shaker which added this vibration leading to the couplet waves. In particle physics, we should have we have here just particles in the macroscopic physics, and there is a resting electron already has angular momentum, and also this there is this clock called Bewegung, the Broglie clock. So resting electron and neutrinos already have some oscillations, and so this way they should create also this couplet wave around as the pilot wave. So instead of external shaker of these experiments, here we should have internal shaker clock of electron, of neutrinos. Yes, and it comes from mathematically, if we put in Schrödinger equation this energy, which relativistically should have contain also mc square as the mass of the particle, then we get the frequency literally propelled by the mass of the particle itself. Yes, and this is called the Broglie frequency. So this is very fast frequency. So for electron, this is like 10 to 21st hertz. So to try to measure it, we would need to slow it down. And there is one such experiment indeed using like 81 1F the clock electrons. This way, the distance between the peaks of the clock agree with the lattice of silicon crystal. Getting this agreement of this clock and the spatial lattice, they get increased absorption. Yeah, so they shoot a crystal and look how many electrons went through. And if for ideal conditions, then there is increased absorption for this resonance between the clock and the lattice. So another question is why these electron neutrinos are oscillating already in the lowest energy state. So it has to be a preference. The preferences in physics are given by energy. So it has to be that energy of these particles has to be minimum, not for omega equals 0, but from some non-zero frequency for electron neutrino, and we can get something like that, for example, in this article. Okay, so finally we have this in quantum mechanics with this wave function, which is the main problem of understanding, I think, is because it combines both the corpuscular nature and the wave nature. Yeah, so it has both the density, square root of density here, and in the phase it hides the quantum phase of the wave part. So there is both, and there are many experiments measuring both natures at once, especially the Afshar experiment I mentioned later. And in these experiments with droplets, indeed they get this orbit quantization mentioned, and indeed the radii are not continuous but discrete because the couplet wave has to become a standing wave. And if they measure statistic of the trajectory now of corpuscular nature, yes, so this was wave nature, this is corpuscular nature. averaging the trajectory of this droplet, corpuscle, they get again quantum-like statistics. So this is wrong. So in fact, we should think about wave function as hiding both the corpuscular and wave nature. Okay, so let's go to the analogs with hydrodynamics, which should start, for example, with electromagnetism. And there is, for example, this Barnett effect that rotating even uncharged object, we get the magnetic field. So finally, there is the analogies usually use this magnetic field as vorticity, a field as velocity of fluid. And this way, the Lorentz force turns out analogous to Coriolis force. Yeah, so we can think about them as nearly the same. And there are many experiments I will mention. So that there will be Zeeman effect using Coriolis force as Lorentz force for the quantized orbit, like here, and Aharonov-Bohm effect proposed by Michael Berre. Okay, so for finally for this analogy, there is no viscosity in electromagnetism, so we need to use assume superfluid, for which there are this nice formula which combines them all. Yes, about the velocity and the quantum phase change and the A field. And here are some two articles showing analogies, especially using this B as vorticity, A as velocity. Okay, so there was electromagnetics. However, what is missing is there are also charges, generally particles. Yeah, so besides electromagnetics, we need to make that the Gauss law doesn't give any real number, but it should be only integer in physics. And then the lightest non-trivial charge is kind of the definition of electron already. Yeah, so the question is how to add particles as these quantized charges, for example. Is not natural answer is topology, and in liquid crystals they indeed get such objects like point-like charges. So here is positive topological charges, negative, so they are quantized by topology, and they can get both the experimental Coulomb-like interactions for them. Also, there are topological vortices, which in particle physics correspond to quark strings connecting quark antiquark and building baryons, nuclei. And there are also this very nice article about building knot structure and showing resemblance with nuclear physics. I could talk along about, but this is another topic. So okay, so let's go to more quantum considered effect Casimir of Casimir. So if you have two planes in Casimir effect, they get interaction. Yeah. So the question is, where does it come from? So here you can see it already in its hydrodynamical analog. You can see the video and articles. So you having these two plates, and again attaching the shaker. We need this vibrational, this external energy source. This, if you do it, the waves between them are constrained by the two plates. Yes, while the outside there are weakened constraints. So this way, the waves between have lower density than the waves outside, what leads to this drift, this attraction. Yeah, so just because of this difference of energy of constrained weight versus less constrained. So we can understand it, however, it is this shaker. So again, the question is, what is this shaker in particle physics? And electrons, we know, has angular momentum, has this de Broglie clock, and it could be this main source of such shakers. We have electrons nearly everywhere. Also, there was these old paintings that also the ships could get this kind of effect and collide. Okay, so another nice experiment as kind of warm up is periodic periodic table of not of nuclei atoms, but this time of droplets. Yeah, so now they are not jumping, just we look at the resonances. So we get two types. So one are radial modes, and another are around. Yeah, so here is fourth. Here are six. Yeah, so we get these two numbers. So the number of around and this kind of no modes, and they can get kind of this periodic table, so kind of atomic nuclei, but just on single droplets. So it's, I think, very nice aesthetic experiment. Okay, so now let's go to the main experiments. Yes, also we get them the tunneling, quantization, and interference. So again, so here is this setting they use, this shaker, and this liquid alone has already this phase diagram. Yeah, so here is the maximal acceleration in G's. So we can see that after four and a half G's, there is something happening. It's called further instability, and then the liquid crystal looks like this. Sorry, the liquid surface looks like this. So we cannot use it. So for the walking droplets, we need to go slightly below. So they usually work in this W phase and very close to this F phase. The closer, the larger memory they call it. So the wave created by this droplet are larger if we are very close to this F phase. So here are some cross sections. So we have time in the horizontal axis, and in vertical there are this position of this surface and the droplet. Yeah, so we can see that in this phase, this B phase, there is one jump every period of this shaker. Here is some period doubling. And finally, this W region is here the most interesting they use. We have every two. So every two amplitudes, the two periods of the shaker, there is one jump of the droplet. Yeah, so they get this kind of period doubling. Okay, so here are some picture. There's some also these droplets get some natural velocity by this interaction with on wave it created. So they're getting like this, like this behavior. So here we can see some photos. So naturally they get some velocity. Also here you can see some droplets jumping in one place. We're getting these spherically symmetric waves. Here it travels. You can see that some interference, both positive and negative, and here it's faster travel. Yeah, so we can see that interesting interference pattern. Okay, so and it can have some trajectory. Here you can see it avoid kind of repel from the barrier of the water tank. So here are two droplets. You can see that they can interact again by this couplet wave. So again, asking, do we need kind of separate wave for each particle? Maybe they use some common wave, pilot wave. If so, the numerics could be much simplified, not requiring to go into gigantic dimensions. Here we can see there is some interaction of two droplets and they start this circulation, which will be quantized. And they can also get crystals of these droplets. So now they interact by this coupled wave, again shared, no separate, instead of the Broglie bond. And they can oscillate in phase or out of phase, and there are nice picture further. And so here is very nice. Here are very nice animations for them. So we can see that there can be in phase or the opposite phase. Yeah. So and they synchronize by this coupled wave that they share. Yeah. So again, so this kind of synchronization may happen also in many types of quantum systems. Okay, and then here is the first orbit quantization experiment, very early in 2005. So I think so. They see these two couplet by shared wave, two droplets, and turns out they are not don't get any diameter and period, but only dots. So we can see that there is quantization. So we get this discretization of space of solution. So and we can this is kind of basic orbit quantization. Also, turns out that they have two types: this one half type and integer type. So there are in phase or the opposite phase. Yes, here you can see that they're opposite phase. Here I seems that they are in phase. Yes, and there's some complicated trajectories. Okay, so we could also perform scatterings of such walking droplets. So here is one droplet, second, third. There is some complicated interaction between them. Here you can see some repulsion from this droplet. Again, here is some common orbits. So we can see this shows that the behavior is extremely complicated. Such simulations require extremely precise knowledge of initial conditions, and there is this problem with chaos. So to practically simulate such scatterings, we later need some statistical physics, some averaging over possibilities. And to do it, we later need these Feynman diagrams also required in quantum field theory as a practical, effective tool to approximate statistical behavior, like scatterings especially. Yes, also why this is classical field theory now. Also, for practical calculations, you will need to use this quantum field theory, like Feynman diagram tools. And now this the double-slit experiment. So to get the barrier, they glue some stripe at the bottom of this tank, and it literally repels the droplet. And here are many trajectories of the droplets. Yeah, so and then they can use statistics of the corpuscle of the particle, and then sound for single slit they already get these interference patterns, and indeed for photons also here's for single slit patterns. Indeed, there are these three stripes. They also got for droplets from statistics of single droplets because of this interaction with this pilot wave couplet. And for double slits, they get this kind of statistics, and here is for photons. Yeah, so they are quite similar. And again, so it is because the corpuscle travels one trajectory, but like here, but it's quite complex trajectory, especially near this seed, because of interaction, because the couplet wave travels all trajectory and pilots the trajectory of corpuscle. So also there is this famous quote of Feynman about double slit, that it contains all the mystery of quantum mechanics, because we can further derive the Feynman path integrals as seeing this as a multiplet, as double slit experiment. So understanding double slit, in theory, we could derive the Feynman path integral formulation. And it was said that we cannot understand it classically, but for 20 years they do it, and there is no problem. We can understand it. Yes, so we have corpuscle which travels, which get the statistics, because of being piloted by the wave, like the bomb interpretation. So I don't see any problem here. So there is no longer mystery here. So also the rest of the particle, according to Feynman's quote, should be open. We should study it. And next is tunneling. Here they get again this barrier by gluing a stripe at the bottom, and they get this tunneling behavior that the probability drops exponentially with the width of this barrier. Yeah, so here is also depends on the velocity of the droplet. Yeah, so the faster the droplet, the easier to cross the barrier. Yeah, so here are some trajectories. So and the explanation is that it's probabilistic. The decision we need to pass the barrier or not depends on the state of the wave, which depends on the entire history. So the entire history in very complicated wave determines if we can cross the barrier or not. I think statistical behavior what leads to this exponential drop of probability. So finally, there is also CSH violation. So one of these Bell-like inequalities, which are said to be always conserved in classical mechanics, that so they do it by having these four small tanks, and the question is where the two droplets will stop. Yeah, so they have four possibilities, and as in this original inequality, they calculate this formula, and classically it is said that should be at most two. While in quantum there is this Zirelsor band 2,883, and they get here for some parameters they get 2,449. So it is not classical in the standard sense, and again, so it's more complicated. So in classical system, it is said we cannot violate it, but this kind of static test is able to violate Bell-like inequalities. Another interesting experiment is this Elitzur-Vaidman bomb testing. So the original thought experiment was like this, that we have this bomb which would be detonated by single photon. But the question is, could we still test it without detonating it, preferably with some probability? So in this interferometer, if you put just one photon, so if it goes to the bomb, it detonates. But if it goes here, we could test existence of this bomb based on the again based on this interference. And here you can also see that so the when the photon detonates the bomb, the pilot wave does not detonate the bomb. Yeah, so and they can also use it here. That here the bomb is recreated as this kind of added fragment. So if the bomb is there, you can see that the blue trajectories go here, and the blue trajectories are the right we are interested in because they don't detonate the bomb. Yeah, so we can see they don't detonate the bomb, they don't get there. But when there is the bomb is not here, we can see that the position has changed. Yeah, so without detonating the bomb, without going to this bomb, we can see that if it was there by seeing if the blue paths are here or here. Yeah, so very similar as this famous Elitzur-Vaidman bomb testing. Then the Sakharov bomb effect, which was proposed by Michael Berry in 1980s and realized first 1999, and a few months I've seen some novel realization. So this is said that this is exactly testing this correspondence that the vorticity corresponds to magnetic field, velocity fluid of to electric field to a field, and we get this Arnold bomb effect, and we cannot see the difference, but some of them are I think those are for electron for the real Arnold bomb, and those are for the fluid, just using the analogy. So the behavior is quite similar. So next type of quantization, so-called random quantization. So now, like previously, we have two particles. Now there is first with one particle. And orbit quantization for single droplet as particle here, but requiring to add this rotation of our tank. Yeah, so now it's shaking and rotating. Yeah, so it's more complicated. So as mentioned, this rotation corresponds to magnetic field. So it's kind of instead of the Landau, instead of Lorentz force to make the electron go in circles, here we have the Coriolis force, which acts using the same formulas practically, but just switching B and omega. So and they indeed get this quantization as so the radii are not continuous but discrete. Yeah, so that they get quantization. So it is one because intuitively because of the standing coupled wave has to become a standing wave. Yes, getting that resonant condition. If it's not standing wave, then there will be fluctuation and we should radiate, going to some near standing wave. As in stationary Schrödinger equation, where also we find its standing wave, yeah, in this stationary version. Here is some simulations. So usually they are very simple, just adding weakening of the weight, the wave, and shifted in time. So we get just add these succeeding circular waves, and they get simulation which work quite nice. So if you have two particles with orbit quantization, maybe they can get Zeeman, yes, and indeed in 2012 they get it using again the Coriolis force as Lorentz force. So instead of magnetic field, they are now rotating the entire water tank, and we can imagine. So there are these quantized orbits. And if we rotate one direction, the radius should increase. In the other, they should shrink. So it is intuitively, but this is Coriolis force corresponding to Lorentz force. And indeed, they get this nice Zeeman splitting of orbitals, but now for classical bouncing droplet. Yeah. So again, it sounds magical quantum, but you can get very similar in hydrodynamics. And finally, there is a double quantization. So to get it is much more complicated because they require this ferrofluid. So the droplet is made of some fluid which is magnetic, and so there is a magnet above. This way, it acts as this harmonic harmonic potential. And thanks of that, they were able to get this not just one quantization, but a double quantization. So both the radius of this orbit, but also of angular momentum. So like in atomic physics, we have triple quantization. Yes, there is n, the n, l, and m. So because we live in 3 dimensions, but here in the round 2 dimension, 2 dimension we have only two. So this l and sorry, the l and n and m. No, and then okay, and then some angular momentum, and here are some trajectories. So the maximal angular momentum trajectories are just circular. Then this lemniscate has zero angular momentum, yes, because the ones in one direction, second direction, yes, also this zero angular momentum averaged. So then there are these kind of solutions, trajectories, and now the blue one. So we can see very nice family of quantized orbits as orbitals. So the trajectory has this quantized orbit, while the coupled wave has quantized quantized orbital. Yeah? So very similar, but in 2 dimensional version of atoms. Okay, so then also get some switching between these between various trajectories. So between them, there could be some switching, some intermittence, so nice chaotic behavior. And then there get them quantum-like statistics. So running such trajectories and recording video and finding the statistics, and turns out it agrees with quantum statistics. Yeah. So again, so like previously we have focused on the wave nature, standing wave, So the wave has to become standing wave. Here we focus on the corpuscular nature, and now the corpuscular has indeed get the quantum statistics is in the square of absolute value of the wave function. So also here is instead of circular, so here was circular, here is elliptic, and they get these two foci. But then they say that it's similar to quantum corals. If additionally adding this shallowing in the tank, so they say this is very similar to popular experiments of atoms. So the every dot is here is an atom, and they can see this again the wave, which is not separate for each particle, but there is a common wave. Yeah. So this one maybe we don't have to go to these extremely high dimensions. Maybe it's sufficient to work in 3 dimensions with this shared pilot wave between all the quantum objects, atoms, electrons. Yeah. And so they say they get similar behavior on these droplets. So okay, so here is another view from this corpuscular perspective that naively we should use diffusion, but diffusion gives very different statistics. For example, if you have 0-1 range, diffusion would say that stationary probability distribution should be uniform there, while quantum mechanics says it should be sign square. It's very different stationary probability distribution in infinite potential well. And we can understand and repair this problem because standard diffusion is based on so-called generic random walk. That if you have a drunken sailor and he sees three possibilities, he uses one third probability. So this maximization of entropy locally, but turns out it's not maximizing mean entropy production, average entropy. What can be done by maximal entropy random walk, which now works on the paths instead of seeing the steps, getting completely different behavior. For example, for this lattice with defects, where this lattice and every node has loop to itself, self loop, until there is this defect shown with squares. So this removes self loops. So this inhomogeneous lattice, like in semiconductor. So it's not that after 10 steps, both random walks give me the same, but after 100 steps, you can see the difference. Yeah, so this is spherical. This is very different. And after 1,000 steps, here we have nearly uniform distribution, while in maximum random walk we have localized distribution. It's completely different statistics aesthetically. And turns out it is exactly as quantum mechanics in maximum random walk. And qualitatively, the difference is huge because if we attach electric field here, there will be electron flow. Here there's no electron flow. So here is conductor, here is not conductor. And in reality, indeed, this is a semiconductor. So it's much more difficult to conduct electrons because of this kind of localization called Anderson localization. And here are some experimental data much closer to this maximum random walk than standard random walk. And now we can go back to this infinite potential well. So to get the sine square, if we assume uniform path assembly of paths from now toward future or from now toward past, some half paths, then we will get first power of the amplitude. But if we go use full paths, so in this moment, literally paths from the past and paths from the future meet, we need to draw it twice. So we need to multiply the amplitudes from the past and from the future, we get the square from the Born rule. It is very similar to S matrix that we need to multiply the propagator from minus infinity and from plus infinity, and they have to meet, and we need to get this product called the Born rule, which what allows to violate Belling inequalities. So this is, I think, the most crucial, where the Born rule comes from, where the Bell violation comes from. Also they get this kind of spin lattices. So they get multiple such shallowing, and there are multiple walkers circling, and they interact between each other, and based on the parameters, they can change it from antiferromagnetic to ferromagnetic. So again, they can get these magnets also this way, kind of analogs. Also, there are some other directions, some multiple types of droplets experiments, but it's quite far. Okay, so at the end, let me briefly talk about some other related experiments. So one I've mentioned at the beginning is the Afshar experiment 2004. So while naively there is this principle of complementarity, that the particle can be only one corpuscle or wave in the one time. But this is one of experiments showing it is both simultaneously. So the experiments look like that they have these pinholes, and here is lattice. So for wave as the corpuscle, it should use the lens behavior. So yes, so for the corpuscle we use the lens, while for this lattice of the bars it should use wave nature, and now we use both. So that it is both the corpuscular nature by the lens trajectory and interference for the pattern. So then the wires are in the dark spots of this interference, and turns out it work that it doesn't reduce intensity, and so both nature at once used are working. So showing that we shouldn't think about particles are having one time wave nature, one time corpuscular nature, but both simultaneously. And a more recent experiment also claiming simultaneously wave and corpuscular nature is this using these nanowires, and they say that they get both this wave nature in this direction and quantization in this direction. So again, getting both natures in one time. And so this is again this clock, so we need it, so it's not so trivial, but I think it can be obtained, but we need to make that particle can reduce energy by activating oscillations, what can be got but by negative Hamiltonian terms which appear in many theories. And it also has some solid state analogs. So there are multiple articles also saying that they observe Zitterbewegung, but now not for electron, but in some liquid some solid state or Bose-Einstein condensate analogs. So then also I have seen one article that's saying that maybe precession is this clock, but I think this is just angular of the wave near electron, that indeed the field is rotating, not point, because point is only perturbative approximation. The field, the non-perturbative, there is only field, and angular momentum should be in the field, what I think acts as the clock of the electron. Okay, so and there is also a very nice experiment. There are multiple now experiments of photos of orbitals. But I think this is the nicest, that we have these atoms of carbon, and there is a large voltage. So now electrons go from this last electron and to the screen, and by the shape of the electromagnetic field, they get kind of lensing. So they say that they can see the shape where exactly this electron escaped from. And getting this kind of s orbital, p orbital clearly, and so on. Yeah, so they get these orbitals by statistics. So every electron went from some position, and they average up to this probability distribution hidden in wave functions. Yeah, so I don't see any problem. So this should be just statistics. Wave function is just statistics, not some fundamental stuff. It's averaging the corpusculum. Also, there's nice video about Bohmian electron trajectories in atoms. And almost the last slide. What about the most magical the measurement? Yeah. So why yes, there is a problem. So we say that we use Schrödinger-Dirac equation, but in fact they don't describe measurement. They just shut eyes for the measurement and open after. Yeah. So if they cannot handle it, that means that we need to go to deeper theories, and deeper there is quantum field theory, which adds fields like electromagnetic. Yeah, so to understand measurement, wave function collapse, we need to, I believe, include fields, especially electromagnetic. And measurement has classical analog, like the Stern-Gerlach, which is not quantum or classical, but we can think about this as classical, because this is just magnetic dipole in magnetic field. And magnetic dipole in magnetic field will precess, because it gets torque by this equation. And precessing means varying electromagnetic field. And varying electromagnetic fields means radiation of energy, like antenna. Yeah, so it should lose energy until it gets to parallel or anti-parallel alignment, where this torque becomes zero. So we get classical measurement. I don't see any magic here. So we just have to include electromagnetic fields around, and it should lose energy getting to parallel or anti-parallel acid measurement. And this is the summary. So the big question is, where is the boundary? And I hope maybe I have convinced that there is no boundary. There's just different perspectives. That you have one system, like couple of oscillators. You can look at this classically on quantum. And so this is trivial. The more sophisticated examples are more difficult, but still everything seems to work. Thank you for attention.